Okay, we're starting Unit 3, and to begin the unit, just like always, one of the things we want to do is focus on our vocabulary. Um, Again, the reason we do this, and I have checks next to everything that feel a typical first-year chemistry student would recognize as a term they could probably understand in a sentence. Pluses next to anything that I think a typical average first-year chemistry student would know at this point in the year. And we look at metals, metalloids, nonmetals. Okay, these three here being three terms that I think we could probably figure out if they're used in a sentence. Halogens, noble gases, we've seen them up to this point, haven't really talked about them in depth. Periodic, I think generally speaking the term periodic meaning regular, repeating, something we've heard before, a periodical. An octet we've talked about, and it even as a musical term. Might know what an octet is, but that 8 is great. One of the things we talked about last unit. States of matter, being the solids, liquids, and gases. We should be familiar with at this point. We have covered them. The diatomic elements we've mentioned. Families, I think we could probably figure out in a sentence in terms of just generally knowing what a family is and how to demonstrate certain properties of a family. I also like to recognize, again, the 13 out of 28 that you see over here is not to make anybody feel like they don't know what they're doing. It's just to make sure we know in terms of prior knowledge, we're probably below 50%. Then, because we're about to get into the history of the periodic table first, we'd like to recognize a very influential person, Chuck Norris, who I don't know if this has been proven yet, but at one point may have destroyed the periodic table because he only believes in the element of surprise. Being a huge fan of Chuck Norris myself, couldn't start the unit on periodic table without having my favorite man front and center. And then, of course, a little bit of texting humor. It's amazing it's already made it to periodic table humor. Couldn't help it. Anyway, we're moving on to the history of the periodic table and what we are going to talk about in terms of periodicity. This word here, it's a long word for what it means to be repeating regularly. The first guy we give credit to in terms of organizing the elements in the earliest form of the periodic table is Dmitry Mendeleev. Now, Mendeleev did what I think most people would do. He was a very smart man, very organized guy who took and organized the elements in terms of increasing atomic mass. And his goal was to group the elements in doing so according to common properties. So he took what he felt was the most obvious way to arrange the elements, that being increasing atomic mass. And we had gaps where there were elements that were not yet found. Sometimes the elements that he did place in different groups and periods were a little bit out of order. We'll find that in his group 1, he does really well with hydrogen, lithium, sodium, potassium, but then you'll see copper, silver, and gold in his group 1, where the modern day version you won't. You'll see cesium, which had not been discovered at that time, and francium, which we still can't isolate a whole lot of, and it's only around for about 22 minutes when we get it because it's unstable. So anyway, back to Mendeleev, he ordered things, the elements, in terms of increasing atomic number, and found that he got commonalities. So elements in this group, generally speaking, except for hydrogen at the top, had common properties. And the same thing for his group 2, 3, 4, and all along. And then he ran into a little bit of a problem over here where he couldn't quite separate these guys out. And what he found was when he got to here, there wasn't another group of elements that shared different common properties. Instead, he found that those properties began to repeat, and he started over. So when he went from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and that, by the way, is dead on across the board until he gets to fluorine and has nothing after that. He found that there wasn't another element to put here, that the process started over again back with sodium. And then it went from sodium to magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, nothing over here, and the process began to repeat back with potassium. So that's where the term periodic comes from. The gaps that you see here, here, another double gap here, these gaps are undiscovered elements. And there are issues in terms of the way that Mendeleev organizes periodic table where things are actually out of order. The guy who came along next, Henry Moseley, used X-ray spectra to prove the existence of the proton. So he was building on Rutherford's discovery that a nucleus existed that was dense and positive. That most of the atom was empty space, but there was a dense positive nucleus. Well, the positive part is that guy. And Moseley determined that there was always a whole number of positive charges once he was able to assign a charge to this particle. There was always a whole number of these charges. And so this became known as the atomic number. Moseley then went on to arrange the periodic table instead of according to increasing atomic mass, according to increasing atomic number. And what happened is, as they would say, the rest is history. What happened is he found that now there were no gaps and things actually lined up very, very well. The group 1 elements, except for hydrogen, all share very common properties. The group 2 elements all share very common properties. He found, or scientists found, this area in here, what we refer to as the transition metals, they kind of buck the trend. The number of valence electrons, which is what we'll find in the next couple pages, is really responsible for causing the similarities and differences between different elements and how they behave and how they bond. Well, these guys jump all over the place. They're anywhere from 1 to 2 to 3 to 4 valence electrons. But then the pattern resumes with group 13, 14, 15, 16, 17, and 18. So you get this repeating pattern that starts with group 1. Group 2 sort of skips over our transition metals. And you've heard me refer to them in class as the teenagers, the adolescents of the periodic table. How they behave is totally dependent on what they're with, who they're around, what their peer elements are, and their behaviors vary based on what different elements are present with them. And then the pattern resumes for 13, 14, 15, 16, 17, and 18. And again, this really, really solid pattern developed because of the fact that Moseley now arranged the elements according to increasing atomic number rather than increasing atomic mass. I'm going to ask that you guys read through all of this. The periodic law is based on atomic number, the same way the identity of all the elements is based on atomic number. You need to read 1 through 6 in order to understand how and why the periodic table is periodic. What causes that repeating pattern? And the one thing I'll constantly refer to throughout the year is that this periodic function of atomic number is really, really similar to something you guys already recognize, and that's the calendar. And it works great because the way that the sort of the analogy that we'll make here is that a calendar has columns, just like a periodic table does, which we call groups on a periodic table, and it has rows, just like the periodic table, which we call periods when we're talking about the periodic table. And the same way, if you looked at a calendar, you probably could describe how you feel on almost every Sunday, especially during football season. Obviously, being a football coach myself, it's NFL Sunday. There's Monday Night Football, which might be the only positive on most Mondays. And then you've got your Tuesday, Wednesday. Most people can identify on Monday how they feel. Just say the word Monday and you get, nobody likes Mondays except for Monday Night Football. Tuesday is sort of a blah day. It's not Monday, but you're not quite halfway through the week. Then you get to Wednesday. Wednesday is hump day. Kind of feel like Friday's somewhere in sight. You could describe how you feel on a Wednesday. You're tired, but there's a light at the end of the tunnel. Thursday, you're one day away from the weekend. Kind of gives you a little bit of hope, a little extra energy. Then obviously Friday is a big day. Everyone loves Friday. It's the last day of the week that you have to go to school. So who's not happy on Friday? Somebody should write a song about that. And then you've got Saturday. Saturday, no school. I probably couldn't put enough stars on there for you guys on Saturday. And then the cycle repeats. After Saturday, you go back to Sunday, and you're back to staring down the barrel of another Monday. But you can see how it's very easy to associate different emotions with different days of the week. The same way, on the periodic table, these, here it could be our Sunday, our Monday, Tuesday, Wednesday, Thursday, Friday, all the way across a period. You know how you feel on the days of the week, but it's a lot harder to tell how you feel on week 1 of a month, week 2, week 3, week 4. Now, October might not have been the best month to pick because of Halloween, so everyone knows how they feel in the last week of October. Ready to trick or treat. But the point remains that there are a lot less similarities when you think about week 1 of every month versus Sunday, day 1 of every week. So the columns, just like the groups, days of the week, there's a lot of similarity between every single Sunday. You can describe how you feel. But then when it comes to weeks of the month, there isn't as much similarity from week 1 to week 2 to week 3. Week 1 of every month doesn't feel the same as week 1 of October versus week 1 of November. There's definitely not as much similarity there. So that's a little bit more into periodic law, and a good analogy, I think, on how to keep track of how the periodic table works, where the similarities are and where they aren't. What you had to do for homework tonight is work a little bit on the arrangement of the periodic table. I'm going to take you through it. The first thing we talk about are the periods. Those are the horizontal rows running. We always talk about when we say consider the periodic table as you move across a period, we move from left to right, okay? So whenever you hear consider the elements as you move across a period, that means from left to right. What we want to do is sort of solidify the idea that the periodicity, the periodic nature, is based on increasing atomic number, and that the behaviors, similar behaviors of the elements within a group is based on bonding and the number of valence electrons. So as we consider this period 4 with potassium, from left to right, the element name for K, as we said, is potassium. The group number, it's group number 1. the electron configuration would be 2, and these are all things you can find on your periodic table. The electron configuration would be here on your periodic table, in your reference tables. It's 2-8-8-1. Group 19, they should add up. 2 plus 8 is 10, plus 8 is 18, plus 1 is 19. The Lewis diagram, you'd use a dot or an X to signify the 1 valence electron in potassium. What you'll do is continue to go through across the period for calcium, gallium, germanium, all the way, and take a look at the similarities and differences between really the electron configuration and the Lewis diagram. That's where I want you to focus. Looking for similarities and differences in the electron configurations and the Lewis diagrams. Then we're going to work on the groups, the vertical columns. You don't need to fill in this first. This is just an illustration. Okay, but what I want you to see is I'd like you to notice they've got these groups all color-coded, and this part in here that we referred to as the transition metals earlier, not coded. That's because we don't assign real true group numbers to these guys. They get kind of a 3A and 4A and 5A and 6A all the way across. The groups as we define them in chemistry on the periodic table are groups 1, 2, 13, as we said before, 14, 15, 16, 17, and 18. And then this group, or group of groups, the transition metals, sort of avoid them for now because they don't participate in that whole periodic function business that we're working on right now. So we're going to kind of leave them off as we talk about the groups, and we'll come back to them later. So we'll start again. We want to focus in this little exercise on electron configuration and Lewis diagram. All right. So for the element name, these are all the elements in group 1. H would be hydrogen. The electron configuration, simplest one we can get, is 1. And then the Lewis diagram would be an H with a dot or an X. You're going to continue to go through, do the same for the rest of the elements here. Again, focusing on electron configuration and Lewis diagram, looking for similarities and differences. And then you'll finish up with a practice, and we will go over this all tomorrow to start the class. So make sure you're writing down any questions you might have, and we'll see you bright and early tomorrow.